Okay, good morning.
Good morning, sir.
Okay, so I had a power issue, so I joined late. So some problem with the UPS. Okay, now it is solved. Okay, yesterday these are the things that we understood. So how to call uh, a subroutine which is defined in assembly code from the C code, and how to call the C library calls and the subroutines from the assembly code. Okay, these are the things that we went through, and the argument passing also we understood. If you're passing more than one argument from the C code to the assembly code, okay, while calling the function which is defined in the assembly code, so we understood how the registers get filled in. So the first value gets goes to the register R0, and if there are two arguments which are passing, then the first argument goes to the R0 and the second argument goes to R1. Okay, uh, and then yeah, this was the thing, and we also understood how to compile the ARM assembly code. Sorry, how to compile the C program using ARMCC, how to assemble the assembly code using ARMASM and generate an output file. So profiler, instruction scheduling. So this fetch, okay, all these things was done. Now we got to continue our discussion from here. So this was the last thing that we understood. This example is showing why the branch instruction takes 3 cycles. 3 cycle stalls, why it is. So 3 cycle stalls is required because we have one instruction for computing the address of the target instruction, 1 cycle for computing the address of the target instruction, and 1 cycle for flushing the pipeline to remove the faulty instruction that I have entered into the pipeline, and one more clock cycle for letting the target instruction enter into the pipeline. So now we'll try to understand how the instruction scheduled with this example. Now here I'm taking the example uh, a C code which is written here. What this C code is basically doing is converting a string which is written in uppercase to the lowercase letters. Okay, so what we are doing here, say this is the memory location, and I have A, B uppercase letter, C, D stored, and N is pointing to this. I have another memory location, A, B, C. Sorry, I need not take here. Now we have out pointing to this. We have out pointing to this. Now what our program does is, so it's going to copy this string which is in uppercase to this memory location in lowercase. It converts them into the lowercase. So you can see here. So I'm reading the character to which N is pointing. I'm assigning it to C. C gets A now. A. Okay. Now what I'm checking, if C is greater than, so or equal to, inside the single quote we have written A, uppercase A. Now inside the single quote if you write, it takes ASCII value of A. Okay. ASCII value A is 65. Uppercase A, it is 65. Now I'm checking this A is also 65. C is also 65. 65 greater than 65. And uh, C is less than or equal to uppercase Z. Uppercase Z ASCII value is 96. So these ASCII values you got to remember. Okay. And for lowercase a, it is 97. 97. Okay. Now what you're doing here, so you're checking whether it is greater than a, and greater than or equal to a and less than or equal to z. What does it mean? So it is uppercase letter. Now here you come, and then what you're doing, C plus a, uppercase lowercase a, it is 97. So 97 and C is 65 plus, and this uppercase is A is again 65. Okay, so 65 plus 97 minus 65. 97 minus 65 is how much? It is 32. Okay, so 32 plus 65 is how much? 97. 32 plus 65 is 97 again. So which is the ASCII value of lowercase a. Now what we have, so this uppercase a, the character C is equal to a. Now it is converted into lowercase a, and we write this lowercase a to this memory location. Okay, out is incremented again. It is pointing to this memory location, and in is also incremented, and it is pointing to this memory location. Okay, so this is post increment, and this is also post increment. Now go back again. So what gets assigned to C is now B. C is equal to B. C is B right now, and then so you're checking again. So B ASCII, uppercase B ASCII value is 66. For uppercase A it is 65. Uppercase B it is 66. 66 is greater than or equal to 65, and 66 is less than or equal to 96. True. Now you come here. So this is 66 plus 97 minus 66. Now 97 minus 65. That is again 32. So 66 plus 32 is how much? 66 plus 32 is 98. 98. So 98 is the ASCII value of lowercase b. Okay. Now this uppercase b we have it converted into lowercase b, and where it is written. So C, and then character C I'm assigning it to this memory location. So hope people are able to understand.
Yes, sir.
Okay. See the ASCII value of uppercase A is 65. Uppercase A is 65, and for lowercase a it is 97. For lowercase a it is 97. It starts from here, it goes like this, and uppercase B it is 66, and for uppercase Z it is 96. So till 96, and now we have the ASCII value of lowercase a starting from 97. ASCII value of lowercase b is 98. It goes like this. Okay. Now, so this is what is the C level program, what we are high level program, what we have written. So, but to understand the scheduling of the load instruction, we need to convert this into the equivalent assembly code. With the assembly code, you can easily understand the scheduling of load instruction. Now, when we're dealing with the assembly code, all these ASCII codes which are in the decimal. So the 65 is the decimal ASCII value of A. So we got to convert this into hexadecimal value, because assembly code always deals with the hexadecimal values. Now what is the hexadecimal equivalent of 65? It is 41. Is that correct?
Yes, sir.
Okay, 41. So let me go here, and this is the equivalent assembly code what we are writing. So what we are doing here, your R1 is something like in pointer. R1 is something like in pointer that we understood in the previous class, and R2 is C, the character C. Okay, and other one R0 is your out pointer. Okay, now what we are doing here, so you can just observe, I'm loading the content pointed by R1 R in to the register R2, and then I'm post incrementing it by 1 byte. Next, what I'm doing, see here, from C, from the value which is there in register R2, I'm trying to subtract this 41. Now what is this 41 is? 41 is the hexadecimal equivalent of the ASCII value of uppercase A. ASCII value of uppercase is 65, and the 65 hexadecimal equivalent is 41. So hope you people are able to understand. Hello?
Yes, sir.
Okay, so C minus A I'm doing. Next, here I'm comparing this R3, the subtracted value, with 19. Now what is this 19 is? What is the decimal equivalent of 19? Hello? What is the decimal equivalent of 19? Hexadecimal is 19. What is the decimal equivalent of 19?
25, sir.
25.
See, Z minus A. What is uppercase Z is?
96.
ASCII value of uppercase Z 96 minus 65. How much you are getting?
25.
30. How much it is? 31. Correct, huh? So that this is 31. So I'm checking. So comparing R3 with 31. Okay. And then add LS this. So what is that I'm adding? This 20. 20 is nothing but your 32. This value. So this value. Okay. Now with R2, which is the difference value here, and I'm checking if R2 is lesser, okay, lesser than, so then store it into the memory location. Which memory location? Where R0 is pointing. R0 is nothing but this now. So R0 is out and it is pointing here, and what it writes there is the lowercase letter. So uppercase letter is converted into the lowercase letter and it is written. So this is what is an equivalent assembly code for this I level C code. Okay. So first I'm checking here if finding the difference C minus A, assigning it to R3, and next I'm checking whether C is less than or equal to difference of these two. So if that is true, okay, and then I perform add with the condition LS lesser than this 32 I add. So then the result what I get in R2, I'm storing it into this memory location. Now R2 will be holding the hexadecimal equivalent of the ASCII value of the lowercase letter, the corresponding lowercase letter, and that is what gets stored into the register R0. And this is all fine. So we are comparing with 0, and then branch and not equal to str lower. Okay, so we keep repeating the process. Okay, and then while returning, we load the content which is there in register R14 to PC. R14 you can write, or else you can write it as LR. Now this program, what is written here, the assembly code, we are scheduling it for execution. So when I'm scheduling it for execution, so just observe this LDRB now, R2, R1, 1. So output register is R2. Is it used as input here in the next statement? Yes. That means the subtract instruction is dependent on LDRB. So 1 second. This subtract instruction is dependent on LDRB. So in the previous class, we understood the load interlock problem, because subtract instruction is the very next instruction after the load instruction. Now there is the load interlock problem. Now how many clock cycles this subtract instruction has to wait in the execute stage to get the data? 2 cycles, 2 cycles, stall cycles. Now if this is in the clock cycle number 1, so clock cycle number 2 is a stall, and clock cycle number 3 is again a stall. Why? Because we have already understood this here. Here we understood it. So 2 cycles stall. Okay. Here in that example, instead of add instruction, we have subtract instruction, which is immediately dependent on the load instruction. So 2 cycles stall. And next, the rest all. We are focusing only on this load instruction. Okay. Focusing only on the load instruction. And we assume all other instructions can, they execute in the subsequent clock cycles. So only subtract instruction has to stall for the 2 cycles after LDRB is executed. So after, if I assume LDRB executes at first clock cycle, so we can have the subtract instruction executing it in the 4th clock cycle. So because 2nd and 3rd is a stall cycle, 5, 6, 7, 8, and next again we are focusing on the branch instruction. So branch instruction, I said it takes 3 clock cycles. So 1 cycle for computing the address and 2 cycles for 1 cycle for flushing the pipeline, another cycle for letting the new instruction and target instruction enter into the pipeline. But both the things you can write it as flushing itself. So these are the 3 cycles, and that means only one cycle is useful cycle, that is computing the address. But the other cycle 10 and 11 are the waste cycles, which are used in order to flush the pipeline and load the target instruction. Okay, so right now one iteration of this loop, okay, one iteration of this code segment is taking 11 clock cycles. So just one iteration is taking 11 clock cycle. So if there are 4 characters in my string, okay, say like this, as I wrote earlier, A, B, C, D. Now this loop, how many times it gets executed? 4 times. So 4 into 11. So I require 44 clock cycles to perform the execution of this code segment. Okay, to convert all this my string A, B, C, D to lowercase. So this is what the original. Okay, so 2 cycles are wasting here and 2 cycles are wasted here. Okay, so totally on every iteration we have how many clock cycles wasted? 4 clock cycles are wasted. Okay, so like this it goes for 4 iteration. So 4 into 4 is 16 clock cycles. Okay, 16 in this 44 clock cycles. So 16 clock cycles are just the overhead clock cycles. Okay, so the clock cycles which are used for what the stall cycles which are spent on stalling the pipelining. Hope you people are able to understand. And 44 minus 16 if you do, okay, how much it is? 8, sorry, 14 minus 6 is, yeah, 8, and this is 3 minus 1, 2, 28. Only 28 clock cycles are useful clock cycles, and this 16 clock cycles are used for what? Dealing with the pipeline stalls and the branch instruction. Hope you people are able to understand.
Yes, sir.
Okay. Next, what we do, we are modifying our program. So what is a modification? I'll show you. So this is the thing. There are 2 techniques which you can use. One is preloading. Preloading is one technique, and loop unrolling is another technique. So first we'll try to understand the preloading. So here, this LDRB in the previous example, it was inside the loop. So if you go here, see str lower, this is where the loop started, and LDRB was inside the loop. Now in my example, in the second example, I'm just enhancing my program or optimizing program, and I've written this LDRB outside the loop. Okay, LDRB is just outside the loop. That means I'm just preloading the data. Even before the loop start, I'm preloading the data. So what is that I'm doing? So the first character that is pointed by the in. So in is made as an alternate name to register R1, and out is made as an alternate name to register R0. And here we have CNT. Okay, so R2 is the C and R3 is T, temporary register. Okay, you can see here now. I'm preloading, and after that I'm subtracting, comparing, all the same logic till here. Now after this, instead of compare instruction, I'm using TQ, and this we have already understood in our earlier classes. Okay, TEQ, test equality, and here, okay, I'm preloading again. See the data required for the first iteration, the character required for the first iteration, I'm preloading it before the loop, and the data required for the next iteration of the loop is preloaded in the previous iteration. Okay, in the first iteration itself, I go for loading the data that is required for the next iteration. You can see this LDR, NEB. So N again, I'm loading it into C. So here what I do, I convert the first uppercase letter into lowercase letter and then write it into the memory. I'm still in the first iteration. So in the first iteration, so I load the data to C and keep it prepare as the input for the next iteration. And now when it goes back, the data C is already available and it continues. So this is what I'm doing. Now by preloading, so I can go for avoiding. So you can see here LDRB. See, so since the data is preloaded, so there is no stall cycles because of the load instruction. As we saw 2 cycle stall here, that cycle stall is not here because this is data is preloaded. So 1, 2, 3, 4, 5, 6, and again this is also preloaded. Okay, and this BNE, so you might ask, sir, this is load instruction, and this BNE is not dependent on this. BNE is not dependent on this. So now again, there is no stall cycles required. So 1, 2, 3, 4, 5, 6, 7, 8, 9 it goes, and but 2 flush cycles are required for what? The branch instruction. Now for every iteration, we were able to save 2 cycles here. Earlier, on every iteration, so there were 4 overhead clock cycles, so which were wasted. So now we have reduced that 4 to 2. Only these 2 flush cycles are wasted, and the remaining, so we have reduced by just optimizing our code. So now 9 clock cycles it is taking. Every iteration is taking 9 clock cycle. So 9 into 4. Okay. So how many clock cycles? So earlier it was 44 clock cycle. Oh, yeah, here. So 4 into 11, it was 44 clock cycle. So now it is 9 into 4, so which is reduced to 2, so 36 clock cycles. Okay, so it reduces to 36 clock cycle. That means the for the 4 loops to convert my ABCD to lower case, so I require how many clock cycles? Only 36 clock cycles. Okay. Now the same thing is written here. So with respect to the one iteration. So one iteration, the first iteration, one iteration in the original code without any optimization, this code was taking 11 clock cycles, 11 clock cycles, and the code after optimization, this with the preloading technique, so it is taking 9 clock cycles. So 11 by 9, it is now the optimized code. So this code is how many times faster? So this code is 1.22 times most faster than the original code. Understood?
Yes, sir.
Okay. Next. This is we applied the preloading technique, and we were able to get the improvement in the program performance. And what is that improvement in the program performance? So now the program, after optimizing using the preloading technique, is how many times faster than the original program? 1.22 times more faster than the original code. So now I still go for optimizing my program by using another technique called as unrolling technique. Now what I'm doing here in the unrolling technique, I go for unrolling the loop into multiple times. What is the meaning of unrolling? It is something like this. Say for example, I have a loop for, so let me write a for loop. So let us make you understand here. So because if you got to understand the concept of loop unrolling. So for I is equal to 0, I less than 10, I plus plus. And I write some statement here. Say I is equal to I plus 1. Okay. Now how many times this statement gets printed? So 10 times. So 0 to 9, 10 times it gets printed. Now, so what I can do is every time this loop is checking, I need override. So very difficult to understand with respect to the high level statement. You cannot clearly understand that. So let me take this example itself and show you. Say this is a loop now. So here you're going back to the loop here. Okay. And these statements are repeatedly executed. So this from here to here, they get repeatedly executed because they are inside the loop. Say for example, ABCD I have written. I want to convert this, my string, which is in uppercase ABCD, to lowercase ABCD. Okay. Now these statements, how many times they get executed? 4 times. Okay. Now to achieve this 4 times, I'm writing this loop. Okay. Branch are not equal to loop. But this loop is creating overhead. What is that overhead? So these additional flush cycles are required. So is it possible for me to avoid this BNA? So if I avoid this loop, what is that I need to do? I need to go for repeating these set of statements. How many times? 4 times. Hope people are able to understand.
Yes, sir.
So this BNE is creating overhead. What is that overhead? So this BNE I have written for my convenience. What is that? So I'm not able to repeat this for 4 times. So I want to leave the burden on the processor. So I'm writing this branch instruction. As long as this condition is true, you keep repeating this. That is what I've written. Now, so that is the burden on what? The processor. Because every time BNE is called, it has to flush the pipeline by spending 2 additional clock cycles. Now what I'll do, okay, let me not burden the processor. Let me burden myself. Okay, how? So what is the burden I'm taking? I go for repeating these set of statements how many times? 4 times. I replicate it. I copy these statements and I remove this BNE. I paste these statements again here. The same set of statements is pasted here and I do the modification. Okay, what modification I do? Now yeah, it's the same thing I write. Only thing is it is incremented and it loads. Okay, it's the same thing. I can repeat it, no problem. Okay. And again, I copy it. So paste it for one more time, third time, paste it for one more time, fourth time. Hope people are able to understand. So I've avoided this BNE. I've replicated my statements how many times? 4 times. Will that do my job? Hello? Hello? So please talk.
Yes, sir.
So will it do my job? Yes, it does. Only thing is branch looping construct I'm not using. So I've taken the burden and I have made my program length bigger. So because I have replicated the same thing 4 times. So if my string, say for example, the string which I want to convert from uppercase to lowercase is of 5 character length. Now how many times I got to replicate this itself? This time 5 times I got to do it. Now all the 5 times, are we avoiding the branch instruction? Yes. So since we are avoiding the branch instruction, there is no what this flushing cycles. Flushing cycles are not necessary. Then what will happen? The program gets executed in less number of clock cycle. This is what the technique we use. Okay. So okay. Now say this is ABCD is my string. So let me erase everything. So ABCD is my string. Let me unroll the loop for 2 times. What is the meaning of unrolling the loop for 2 times? See, I take this block, I copy it, and I'll avoid this. I replicate my block here, and then I write BNE. Here I write. Hope people are able to understand. So the same exact replica is here. So assume the same set of statements here also, and this BNE is not written here. The BNE is not coming between these 2 blocks, and BNE is written here. Hope people are able to understand.
Yes, sir.
Now this statements are replicated how many times? 2 times. So this is what you call it as 2 times unrolling. Unrolling. So what we have done now? So the loop is unrolled how many times? Loop is unrolled how many times?
2
2
times.
times. Say if I say I want to avoid this BNE for the 3 iterations, what is I have to do? I have to take this block, paste it here, and paste one more block, and after that you put BNE. So now how many times the loop is unrolled? 3 times. Hope people are able to understand. Now since we have unrolled the loop for the 2 times, okay. Now here we are avoiding the branch. So 2 cycles we are saving. Okay, for every 2 iterations, there are 2 overhead clock cycles. So if this BNE, if I write here, and if I write only one set of statement, and if I'm not unrolling it, so then for every iteration, there are 2 cycles wasted. So just imagine now, every iteration 2 cycles wasting, and for every 2 iterations wasting 2 cycles. Okay, hope people are able to understand.
Yes, sir.
So this is what is the concept of loop unrolling. So who does this? Now normally we don't do this. So as a programmer, my focus will be on using the looping construct in order to perform the repetition. Now, have you ever done this kind of loop unrolling job? No, we have not done. We don't do that. Who is going to do that? So the compiler will do that. So compiler, so whatever the code I write, it is not going to take as it is and perform the execution. What the compiler does, it does all this optimization in order to reduce the number of clock cycles taken by the program for execution. So as the compiler, if the compiler is able to optimize the code and reduce the number of clock cycles taken by the program to execute, so what does it mean? The performance of the program is improved or the good, and it executes in less time. Okay, so all this, so preloading and then the loop unrolling, everything will be applied by the compiler. Now you can ask me a question. So okay, what is the maximum number of times it is possible to unroll? What is the maximum unroll that is possible? Is it 2 times, 3 times, 4 times, 6 times, or is it unlimited? No, you cannot have an unlimited unrolling. Unlimited unrolling is not at all possible. Why it is not possible? Because unrolling is completely dependent on the registers, availability of the registers. So if I say 2 times I'm unrolling, I got to see whether to unroll the loop, there is registers available for using it in 2 times unrolling. So we have limited resources or registers, say 14 registers. So 16, but in that 16, 2 are reserved and we can use only 14 registers. So within the availability of the register, the compilers will decide so how many times a loop can be unrolled, whether it can be unrolled for 1 time or 2 time or 3 time. Okay, so there is a limitation. What is the limitation? Is the registers, availability of registers. So why availability of registers is limiting? Because on every unrolling you have to go for using the different register, and you should not use the same register which were used in the previous unrolling. So because of this restriction, so the number of times the loop unrolling can be done is not unlimited. It is limited, and it is limited by the availability of the registers. Hope you understood.
Yes, sir.
Okay, so now come here. Now that is what we are doing here. We are going for unrolling it here. Now how we have done the unrolling, I'm showing you. So 3 times we are unrolling here. 3 times. Say for example, what I'm doing now. So I go for so I want to convert the 6 characters which are in uppercase to lowercase. So this loop, how many iterations it should go? So this loop should go for 4 iterations. Okay, so 6 iterations. So now what I do, and for every iteration we have the BNE called. So now what I'm doing, so here I unroll the loop for 3 times. So that means BNE is used only after 3 iterations. See here. So first what I'm doing, using in, I'm loading the first character to CA0 and loading the second character to CA1, loading the third character to CA2. Next, I'm doing all this comparison, subtraction, and to convert it from uppercase, to convert this what? So these 3 statements, subtract, compare, and add ls, what they do, they convert the character which is there in CA0. Okay, see this is there in CA0 now. CA0 gets A, uppercase A, and CA1 gets uppercase B, and CA 2 gets uppercase C, is assigned with uppercase C. At these 3 statements, what they are doing, they're converting this to the lowercase. And what is the next statement? See that it's a replica of the same thing. But instead of CA0, we have CA1. Okay. Now these 3 statements are converting this to lowercase b. And next these 3 statements. Sorry, till here. Next these 3 statements. What they're doing? They're converting this to lowercase c. Okay. So now 3 iterations are done here. So have we used any BNE branch instruction? No. And after that, what we are doing? So we are loading, preloading the next 3 data. Okay. See here. Yes, we are storing them. Okay. Here and then here. Yeah, we are storing here. So this lowercase a. So this is for the next thing I'm showing you here. So this is for storing. This is for storing. So this much. Now I'm taking this a. I'm storing it into the memory location where out is pointing. And then b, and then c, and then yeah, a, b, c. Next we have written b and a. That means, so without writing this b and a, how many iterations we did? How many iterations we did? 3. 1, 2, 3. 3 characters are converted. Now I have the b and a. Where it goes? Back here. Now what CA0 gets loaded with? D, and this gets loaded with E, and this gets loaded with F. Hope you people are able to understand.
Yes, sir.
And the same process is repeated. This is what is loop unrolling. Now, can you just tell me how many times the loop is unrolled? How many times the loop is unrolled here?
3 times.
3 times. The loop is unrolled for 3 times. So loop is unrolled for 3 times. Now, can it be unrolled for 4 times? See the maximum, see the register what you have used. So 0 is used, 1 is used, 2 is used, 3 is used. Okay, 4, 5, 6, 7 we are not using them. And then CA1 is used. Okay, CA1 is R12 and CA2 is R14. So similarly, there are other registers. So 4 to 11 is still not used. So you can go for unrolling so many times until this register 4 to 7 is also 11 is also used. So the moment you finish using this register 4 to 11 also, after that unrolling is not possible. So many unrollings you can do. Okay, but this still you can go for unrolling. Okay, so we have done here 3, but still it can be done. So why? Because still the register R4 to R11 is not yet used. So we people understood.
Yes, sir.
This is now we'll go for scheduling this. See now, so the LDRB. See what was we have separated now. What is that we have separated? So this LDRB we are writing inside this LDRB and subtract. So there was a dependency and there has to be 2 cycle stall. Now what is happening now? All LDRBs are written first. Okay, LDRB, and this subtract operation is dependent on this LDRB, and this subtract operation is dependent on this LDRB, and this subtract operation is dependent on this LDRB. But without any stalls they can be executed. Why? Because there is this subtract instruction from this LDRB, even though it is dependent, it is separated by how many instructions? 2 instructions. And again this subtract from this LDRB separated by so many instructions, and this subtract from this LDRB separated by so many instructions. Correct? No? So by the time the subtract instruction gets into the pipeline and reaches the execute stage, this LDRB, what it will do, it will write the result to CA0. That is register R2. Hope people are able to understand what I'm saying.
Yes, sir.
Okay, so first this LDRB goes into the pipeline. So what next goes this? When this is in decode, this is in fetch stage. Okay, in the third clock cycle, what happens? When this is in execute, so this is in decode and this is fetched. Okay, and when this goes for LS1 stage, so this is executing, this is decoding, and this is fetched. Okay, this is still fetched. And by the time this goes for LS2 stage, what is the status of the subtract? It is in the decode. Okay, and when this is going to enter into the execute stage, next clock cycle after this completely finishes its execution, that by that time, so the subtract instruction must see the value in what? CA0. So no dependence, no stall is required. Hope people are able to understand what I'm saying.
Yes, sir.
Okay, now based on that, we're writing the clock cycles here. So you can just see now, say this is in clock cycle 1 and this is in clock cycle 2, clock cycle 3. Now the subtract instruction, even though it is dependent on this, so we are performing the execution of some useful instruction here, and this dependency we have separated by some at least some distance. Now this can, without any stall, it can go for executing in clock cycle number 4. So if I don't schedule them here, Okay, if I write the subtract instruction here, then it has to be a stall. There has to be a stall of 2 cycles. Now, without wasting those 2 cycles, I'm scheduled some execution of some useful and independent instruction. And this you can see LDRB CA1. This is not dependent on this, and again this is also not dependent on this. That means they can be scheduled here. Okay, and then again everything, and now we have only 2 flush cycles here. So BNE is appearing after 3 iterations, and 2 flush cycles are required. Now, how many iterations are completing in this 21 clock cycles now? It is 3 iterations. 3 iterations are in 21 clock cycles. Now each iteration is taking how many clock cycle? 7 clock cycle. My original program, without any optimization, this program was taking how many clock cycles per iteration? 11 clock cycle. Now my modified instruction optimized program with loop unrolling technique, per iteration how many clock cycle it is taking? 7. So 11 by 7. Now it is the performance of the program is 1.57 times more faster than the original code. So the performance of this program is 1.57 times more faster than the original code. Okay, so when I applied only the preload, it was 1.22 times more faster. Now after I apply the loop unrolling technique, the performance of the program is 1.7 times more faster. So 3 iterations 21. So 1 iteration is taking 7 clock cycle. Now hence the performance of the code with the loop unrolling technique is 1.57 times most faster than the original code. Is that clear?
Yes, sir.
Okay. So if you have any doubts, please ask me. Yes. So if you have any doubts, please let me know. I'll clarify. So all of you understood?
Yes, sir.
So just all of you once unmute and say.
Yes, sir. Yes.
Yes, sir.
Okay. Okay. So you've understood 2 techniques here for optimizing the code. One is the loop unrolling technique, and then the preloading. See, these 2 flexibility you have when you're writing the code in assembly language. Okay, if you're writing the code in high-level statement, so this direct control of this loop unrolling technique and preloading is not available. Say C code, I'm showing you the C code here. Now, so if I ask you, just do the loop unrolling on this, can you do? No, not possible. It cannot be done. You cannot do the loop unrolling here. So loop unrolling, so you can do by yourself when you're writing the code in the assembly language. Okay. So, but on the high-level language, you don't have that control to do the loop unrolling and all. So you got to wait. So you got to do it using the assembly code. So here you can very beautifully do the loop unrolling. So next is register allocation. I think this we have already discussed, and you people know this. 16 visible registers are available, and 14 are the general purpose register, which are used to hold the data. R13 is a stack pointer, and R15 is a program counter, and R14 is the link register. And then whenever you're using and operating the processor in the thumb mode, so it has to follow this standard. So ARM thumb procedure called standards. So and this standard also says that so whenever you call the procedure, so the register R4 to R11 they must be preserved. And this ATPCS also says that so whenever you are using a stack, the stack must be 8-byte aligned. That means you should go for pushing the elements onto the stack to address which are multiples of 8 bytes. So whenever you're pushing a new element to the stack, it always gets stored at the address which is multiple of 8. That is what is 8-byte aligned memory. And then okay, so another one is a template for optimized assembly routines requiring many registers. So if there are many registers, okay, required whenever you're calling the functions, so then you can go for storing all those registers inside the stack. Okay, store them into the stack, and again you can get them by using the load instruction into the register. Uh, this is one thing. So stack is the one that we use whenever you need to pass too many register content. Okay, and this okay. ARM5 and above, you can use the preceding template even when being called from the thumb code. So the same template works fine for both ARM mode and also the thumb mode for the version still ARM5. Okay, so till the ARM version 5, but ARM for ARM4 and below, we got to make use of the following template. So that means instead of this, what is that? Yeah, instead of this statement, okay, so we got to write it as, so after that statement, we got to write it as BXLR. So this is for the thumb code. Okay. Then allocating variables to the registers. So this I've already told, you know this. While writing the program, henceforth, till now we were using directly the register numbers R0, R1, R2, something like this. To make your program more meaningful and readable, so then you can also go for assigning the alternate names to the registers. So by using the assembler directive Rn, say for example, I is the alternate name I need to give for the register R0, then I write it something like this, I Rn0. Now I is the alternate name which uh, used to refer the register R0. So this is also possible, and this is one more thing which you can use for increasing the clarity and the readability of the optimized code. Okay, and why this alternate naming for the registers is necessary? Okay, and there are several cases where the physical number of the register is important. So few cases to make the program more readable, then we can go for using an alternative name, something like this, variable name. So, but that there are certain cases where the physical number, that is R0, R1, R2, that itself is important. So one is argument registers. So So the first four arguments to the function are placed in R0 to R3. So this is as per the ATPCS standards. Okay, and further arguments are placed on the stack, and the return value is placed on the register R0. Now in this case again, you cannot make use of an alternative name. So what you got to make use of only the physical register number, something like this. And registers used in the load and store multiple. Okay, load or store multiple. Again, for load and store multiple also, so we prefer using the register numbers instead of the alternate names. So even for the load and store double also, okay, double word, we go for preferring using the physical register numbers than compared to the alternate names. And next, okay, from here we'll discuss it in the next class, how to allocate registers when writing the assembly. So we have few more examples. So I think I need another 3 classes, 2 to 3 classes to finish all these things. We'll stop here. From here we'll continue with the tomorrow's class. 350, 43, 135, 56 is absent. 10, 16 is absent. 39, 116, 134 absent.